Hey everybody, welcome to this lecture 8. We're going to be going over radioactive decay and some nuclear reactions. So I'll pull the PowerPoint here to get started. Great. All right, so to start it off, we'll work on a little quiz here from the last lecture. Go ahead and pause this and see if you can answer that. All right. Sounds good. Okay, let's find my mouse here. Awesome. All right. Okay, so there we go. The answer is A, right? In order of decreasing size. So if you remember, as you move to the right across rows in the periodic table, you decrease in size. And that's because the electrons are in the same energy level. But as you move to the right, you get more protons in the nucleus. And so they're pulling those electrons tighter in to make the atoms actually smaller. All right, go ahead and try this one as well. Okay. All right, so in this question, you might have expected the same trend, because if you remember, as you move to the right, the ionization energy increases. But if we look at this graph, the kind of the exception spot, right, at least for the second row, you have between nitrogen and oxygen as an exception, and then also back here between beryllium and boron. And that has to do with the orbital diagram. And if you kind of forgot about that, go ahead and watch the last lecture where we explain that a little more in depth. Okay, so in this lecture, we're going to be talking about radioactive decay, right? So the reason that you have radiation or radioactive decay is that the nuclei and some of the elements, or atoms I should say, are not stable. And so they actually will break down, and as they do that, they release energy. So we're going to talk about 4 different particles or decay processes that can happen. So the first is an atom could lose an alpha particle. And this is where the nucleus shoots out 2 protons and 2 neutrons. So you sometimes see it written either, usually it's kind of like this. So if you remember from the element symbols, right, the bottom number is the number of protons, and then the top number is the number of neutrons. Or sorry, not the number of neutrons. The top number is the mass that comes off, right? So if we have 2 neutrons and the total mass is 4, then we also have, we have 2 protons. The top number tells us that we have a mass of 4, so that means we're also losing 2 neutrons out of the nucleus, okay? It's also written like this, just because helium, you're really losing the nucleus of a helium atom when this happens, okay? So it can also be written like that. The next one is a beta particle, okay? So considered a high energy electron. And the way I think of this one is we actually have a neutron, okay, that splits into a proton and an electron, and then the electron is shot out, okay? And this will make a little bit more sense later on, but that's kind of the way that I like to think about this one. So high energy electron coming out, and the source of that electron is a neutron converting into a proton and electron, and the electron flies out, okay? And then a positron is actually a high energy anti-electron. So you can kind of think of it as the opposite of what's happening here. So you can see that you actually have a +1 in the symbol here. And these numbers that you see here are going to make sense later when we talk about the nuclear reactions. So I might just wait till then to explain these a little bit more. And then the gamma ray is just a high energy photon. And photons don't have any mass, so their symbol is generally written with a gamma. So this is a gamma symbol, okay, the 0, 0. Okay, so remember these symbols. The most common ones you have for alpha, you'll see this. For beta, you generally see this. And for positron, you generally see this right here. And then for gamma, you see usually this, okay? So you'll see those coming up here, but just be aware that there are different ways that these can be represented. Okay, so the whole reason that radioactive decay occurs is nuclear stability, right? Everything wants to move to a more stable state. So on the next slide, I have this graph that I'll show you, but sorry. So in the nucleus, right, you have a bunch of protons with positive charges, and you have a bunch of neutrons. You don't have any negative charges. So generally, you think that the protons are always just repelling each other, right, and it becomes unstable. So the neutrons actually help stabilize the nucleus, and there's these terms, quark and gluon interactions. We're not going to talk about that much, but basically the ratio between neutrons and protons is really what's important to help keep a stable nucleus. And if that ratio is off, then you're going to have some radioactive decay. So the green dots right here, these represent a stable nucleus. So we have number of protons on the x-axis and number of neutrons on the y-axis. So for example, I guess if we went to like this point right here, okay, so for whatever element this is, 60 something, okay, 60 something protons to 90 neutrons is a stable atom at that point. Generally, back here, you can see this line right here represents a 1-to-1 ratio. So at the beginning of the periodic table, all the way up, you know, through almost around, you know, almost to 20, you know, between 0 and 20, basically, the number of protons, I just mixed protons and croutons together. The number of protons and neutrons are about the same for a stable nucleus. But then as you get bigger and bigger, you start needing more neutrons to proton ratio in order to have a stable nucleus. But if the atom, for example, is sitting out here, right, so it's off the ratio a little bit, it's going to be spitting out radioactive particles. The nucleus is going to be unstable. It's going to be doing that so it can merge back into the more stable area on this graph. And so that's kind of why it's happening. But anyway, cool. All right, so let's talk about more of the stuff you really need to know for homework and tests and stuff like that. So radioactive decay, okay, so this equation that I've shown is what you'll see generally in a quiz question, and we'll go over some examples, but the question would say something like, you have this element, okay, Ra, it'll give you the mass, and you may have to look up the atomic number or it just gives it to you, undergoes alpha decay. Okay, so this is going to spit out an alpha particle plus another element, okay? So the real important thing here is just that the number of protons on the right side needs to equal the number of protons on the left side, and the mass number on the right side needs to equal the mass number on the left side. As long as that's good, then you can get most of these questions good. But the principle going on here, like we just talked about, is it's shooting out an alpha particle and actually becoming another element, right? And this happens because element identification is determined by the number of protons, like we've talked about before. So if you're losing 2 protons, you're going to be changing what element that you have. All right, so then beta decay, again, this is, let's see, yeah, so this is when you lose an electron through the process of, right, so I said we take a neutron, we split it into a proton and an electron that shoots outside of the nucleus, okay? So you can imagine this happening in the nucleus, okay? Neutrons converted to proton, and the electron port and an electron, and that's shot out as an high energy electron. So here you have carbon, right? Carbon's number 6 with a mass of 14, which means that the carbon has 8 neutrons. If it undergoes beta decay, right, it's going to become nitrogen, so 7 protons and 7 neutrons because it weighs 14. So you can see carbon is undergoing this radioactive decay in order to have a 1-to-1 ratio between protons and neutrons. If you remember the graph, elements that are like under 20 protons are generally going to want a 1-to-1 ratio. So it's becoming more stable by making this move. And so in the process of the neutron converting to a proton and electron, you gain a proton, right? So that means this is changed to a 7 here. But you don't lose any mass or gain any mass, so the mass stays the same. So that's the principle. The math behind it, right, is just make sure that these numbers are equal on both sides. So we have a 7 minus 1 equals 6, so that equals the 6 protons on the left side. And then we have a mass of 14 on the left side. 14 plus 0 is 14, so we're balanced here, and this looks pretty good. Okay. So, okay, here's just showing this kind of what's happening. A neutron's converted to a proton and a beta particle, which is a high energy electron, basically. Okay. So then for positron decay, what you have going on here is you actually take remember this is kind of the opposite of beta. So the way I think of it is you have a proton that would combine with one of the electrons to make a neutron, okay? And then this would be kind of the anti-electron. It's kind of an abstract thing, but I can get this down pretty good in my head, and then the opposite is kind of true as well. Really what you need to remember is for a positron, you have a positive 1 here in the bottom. So if the question asks, you have sodium undergoing positron decay, you'll put sodium over here on the left, put your positron particle, and then you need to figure out what's going to go here, okay? So one of sodium's protons, right, is going to combine with an electron to form a neutron. And so that means you're going to lose a proton, right? So we went from 11 protons in sodium to only 10 protons, which makes it neon. The reason the mass doesn't change when you convert from a proton to a neutron is because a proton and a neutron have the same mass, right? So your mass isn't going to change when this happens. The only thing that happens is you lose you lose a proton, when you go this way. Okay. So, and then just to double check if you're writing this out, like a homework question or a test question, 10 plus 1 would equal 11, which is the same number of protons on the left side. 22 plus 0 equals 22, which is the same mass on the left side as well. Okay, and then if something undergoes gamma decay, I don't have it on here because it's pretty simple. Nothing changes, right? Because gamma decay doesn't have mass and it doesn't have a change in the number of protons. So I guess just to show an example of gamma decay, I think it looks kind of like that. Okay, so we'd have sodium. When we say it undergoes gamma decay, then we would see, it's kind of a boring question, so you don't really see it, but something like that. I think I'm drawing this symbol right. Okay. Anyway, there we go. Cool. All right, so let's go ahead and try this quiz real quick. Go ahead and pause the video. All right, coming back. So we have polonium 212. So this kind of shows you may not have seen this, but when you see polonium-212, this is actually the mass. And the way you could check that, I guess, if you forgot, is look on the periodic table, find polonium, and Luckily it's PO, so it should be pretty easy to find on the periodic table. And you'll see that the atomic number is 84. So 212 obviously isn't the number of protons in polonium. So that's going to be the mass, right? Okay, so we have polonium, which has 84 protons and weighs a total of 212 mass units, emits blank and turns into lead 208. So if we write this out in an equation, we would have 212 polonium emits something, so something comes off, right? Plus we have what it turned into, which is this 208 lead, Pb. Okay, so if we're looking at the numbers and the mass and the protons, we have a 212 and a 208. Well, that's a difference of 4, so we know there's 4 mass units that come off. And we have a difference between 84 and 82, which is 2. So that's 2 protons and a mass of 4, so that's 2 neutrons. So a radioactive decay particle that has 2 protons and 2 neutrons, right? That's going to be an alpha particle. Okay, so that should be the answer here. Awesome. All right, so using this equation, you could, this kind of logic, you can answer a lot of the questions about radioactive decay. Okay, so these are nuclear reactions. Again, you kind of identify the missing fragment like we did in the last one. Sometimes so in this question here, we were missing this fragment, but the question could be framed to say, like polonium undergoes alpha decay, what element does it turn into, or something like that, right? In which case you're given this one and this one, and you would be solving for lead. I think I misspoke. So in this question, we're actually solving for alpha. I think I said we're solving this. Okay, so those are 2 examples. I mean, you could also have a question where it says a certain element X undergoes alpha radiation, so you know that you're losing an alpha particle, and turns into lead 208. So you'd be given these 2, and you'd be asked, what is the element that does that, right? And so then you're just working backwards. But so there's 3 different ways that you could, 3 different types of questions, I guess, you could be asked about this. Okay. All right, just a little diagram talking about it. Cool. All right, particle accelerators. So now we're going to talk about putting 2 things together, an element and a particle, or an element and another element. In the first part of this lecture, we just talked about a certain element undergoing decay. But what can also happen is that you take an element and you hit it with something else, and it actually forms something else, okay? So they often call this like bombardment. So I've never been to a particle accelerator, but basically they're all like these big circles. If you've seen, what's that show? The Flash, right? Flash is like a particle accelerator explosion, right? And everyone gets different superpowers. So you have these elements that are going super fast around here, and then you hit it together with another one, and you create something else. Pretty cool. So in this case, you have oxygen with a mass of 18 that is being rammed with a proton and being turned into fluorine, and then a neutron also comes off in the process. But what you're doing here is you're making a fluorine 18, okay? So you can artificially create different elements this way. It's kind of an application. A lot of you are probably going into nursing or dietetics or something in the medical field, food science, I don't know. But a lot of isotopes that are used in nuclear medicine are created artificially via bombardment. So using that process that we talked about. So doing this, you can create funky isotopes And again, an isotope is an element, or it's basically two elements that have different number of neutrons, right? So carbon, we generally see carbon 12. There's carbon 13, sorry, or carbon 14. Okay, so all carbons have 6 protons, but this one has 6 neutrons, this one has 7 neutrons, this one has 8 neutrons. But maybe you want carbon 11, right? Well, you need to artificially create it. So ramming nitrogen with a proton is going to kick out an alpha particle plus carbon 11, so carbon with 5 neutrons. It's kind of an artificial carbon. So pretty interesting, but there's different ways to make these different artificial isotopes that are useful. Okay. So in nuclear reactions, let's see, we're talking about conservation of mass number. So this is that number that's on the top, right? And then conservation of charge, we're solving for the number on the bottom. We've kind of already talked about this already. And it's the same principle when you have a bombardment reaction like this. If you look, 7 plus 1 equals 8, 6 plus 2 also equals 8, so you're good there. 14 plus 1 is 15, and 11 plus 4 is 15. So on these nuclear reactions with bombardment, the same principles will be followed. Okay. So if we look at this example, let's try and test it out. So you're going to ram a nitrogen 14 with a helium atom. And in that process, you measure a proton coming off and you want to know what was created, right? So we have 7 plus 2 equals 9. And then we have left side. And then on the right side, we already have 1 proton here, which means we need to have 8 protons in whatever is being made. And we have 14 plus 4 is 18 on the left side for the mass. And then we have a mass of 1 here on the right side already. So it means we'd have a mass of 17 here. So we'd have, then we just need to understand which element was created. And elements are identified by the number of protons, right? And the element that has 8 protons is oxygen, okay? So we can figure out what's created in this process. Okay, so we have an oxygen that weighs 17 mass units. Cool. All right, here's another one where we're trying to identify an unknown particle X. So again, this can be a similar process. So if we look at, or go ahead and pause the PowerPoint and try and work this out on your own first. Okay. So we just add up the number of protons on the right side, and we have 112 protons plus 0 is 112. Okay, and then we have an 82 over here. So what do we need? Basically, you need to know what do you need to add to 82 to get 112? Or do 112 minus 82, right? Either way, you're going to get 30. Okay. And then for the mass units, you have 277 plus 1 is 278. And then the difference between 278 and 208 is 70. Okay. So then you just need to know which element is number 30. And I think it's zinc. I don't know off the top of my head. I'm just guessing. So I think it's zinc with, obviously we have a 70. So that means we're going to be either ytterbium or zinc. And I'm pretty sure ytterbium is higher in the hundreds or something. So I think it's zinc. Okay, cool. Awesome. Let's try another example here. So hopefully you're seeing that these are the kind of questions you'll probably be asked to answer on homeworks and tests. A lot of the other information we talked about is the principle behind it, just kind of some cool applications for it. So another important medical isotope is metastable TC99. Identify the unknown particle X. Okay. So in this one, we basically your MO is going to be undergoing radioactive decay into TC, and we want to know which kind of radioactive decay happened. Okay, so go ahead and pause it and try this out on your own. All right, so in order to answer this question, right, we would need to look up the atomic number for MO and the atomic number for TC. Okay, so you'd look on the periodic table and find what those numbers are, and you'd get 42 and 43. So that would just tell you if you have 42 on your mass is staying the same, right? So your particle is going to have a mass of 0. So you know it's either positron, beta, or gamma. But since the mass changed, or sorry, the proton number changed, that means it's either going to be beta or positron. And if we have 42 on this side and 43 on this side, then we're going to need a -1 to make these numbers equal on both sides. And that would mean you have a beta particle. Cool. I think this is the last question. Just trying to give you a couple of different examples for the homework. Okay, so a balanced nuclear equation for the alpha decay of curium-243. So if a question like this was on a test, right, I told you don't need to know the chemicals or the elemental symbols past number 20. So since curium is past number 20, I would just give you what the atomic number is, which is 96, okay? So if we're working this out, go ahead and pause it, try and do it on your own before you watch me do it. Okay, so hopefully you're able to work this question out. I'll just go through it here. So curium the symbol is CM, and if you didn't, obviously you may not know that one off the top of your head, but I gave you the atomic number here so you can look it up. So 96, and the mass is 243, and it undergoes alpha decay, right? And we know alpha decay is 2 neutrons and 2 protons. So now we balance the mass numbers on the left and the right side. We have 243 mass units on the left. We already have 4 on the right from this alpha particle. So we would have 239 mass units in the element that it's turning into. And we have 96 mass units on the left. We already have 96 protons on the left, and we already have 2 protons on the right from the alpha particle. So we would have the element with 94 protons, which is plutonium. Okay, all you really need to know is the symbol, which you could look up on the periodic table, and this would be your answer. So, all right, hopefully that made good sense. Okay, moving on. So just a cool application here to finish up. So if you've heard of like nuclear energy, kind of talk about what that is. So you have uranium, right, is generally what's used in nuclear energy. So if you hit it with a neutron, it becomes this unstable uranium, and then it starts to break down, okay? And as it breaks down, one of the products is energy that's released. It's kind of a chain reaction that's going on, and you keep releasing more and more energy as it keeps breaking down further and further. So this is what's happening in nuclear power plants, okay? Probably heard of those. And we're not really going to go into the whole process here, but just kind of giving you a general idea. What I think is interesting is energy density, looking at different ways that we get energy. Lead acid battery is kind of an old technology, but you only get 0.02 kcals per gram of the lead acid battery. Lithium ion battery is some of the more modern batteries that we have. You get 0.17 kcals per gram. Carbohydrates, right, in our food actually have a lot more energy per gram than a lithium ion battery, which I think is interesting. Gasoline we're familiar with in our cars, right? And we know that gas holds more energy per gram than batteries, right? So like a battery powered car has a lot of weight in batteries and doesn't have the range that a gas powered car would, right? So that's kind of obvious. Gas holds more energy per gram. But what I think is interesting is nuclear power. Okay, so this is crazy, but 19 million kcals per gram of uranium-235. So That's crazy. It just kind of shows you how much energy is actually packed into some of these molecules when you look at it in relation to like gasoline or a battery. So, all right, I think that'll do it for this lecture. Next lecture, we'll be talking about half-lives and how to calculate those. And we are coming up on exam 1. I know it's crazy. It's only been like the first week. But we're going to be having exams almost every other week this semester. So make sure to stay up to date on homework and lectures so that you have time to study before the exams. I think the first exam opens up right around when you're right around lecture 11, like when a lecture 11 is scheduled. I'll put on the schedule. I don't remember off the top of my head. I think it's like July 6th or 5th or something like that. July 6th maybe. But anyway, coming up, so make sure to just keep that in mind as we're coming towards the end. I think lectures 1 through 11 are fair game, or 1 through 10. Sorry, don't know off the top of my head. But I'll be sending out an email with everything that you'll need to know for exam 1. So that will be the official source of information on that. But about lectures 1 through 10 or 1 through 11 is kind of the material that you're going to need to know for exam 1. Okay. So keep that in mind. Keep up to date on everything, and we'll see you next time.